great things. How many of you are like, good, now we're going to finally learn some chemistry. Who cares about converting units? You want to learn some chemistry. So matter is composed of atoms, and the property of the atoms determines the matter's property. So we say an atom is the smallest identifiable unit of an element. Can't break anything down further than an atom, chemically that is. An element is a substance that cannot be broken down into simpler substances. So like water can be broken down to hydrogen and oxygen, and then you can't break it down any further. There are about 91 different elements in nature, and consequently about 91 different kinds of atoms. I'm looking over there and I see uranium 92. Why are we saying 91? Probably because of technetium. Element number 43 over there is man-made. So if we get rid of that, don't count that one, we get to about 91. Then of course you see all the way over to 118. Those are short-lived, made in a lab, only hang around long enough to say you've made it and then it's gone. The exact number of naturally occurring elements is controversial because some elements previously considered only synthetic may actually occur in nature in small quantities. We don't really need to worry about any of that. So here's John Dalton, and he came up with what we call Dalton's atomic theory, where all matter is composed of tiny indivisible particles called atoms. There was a Greek philosopher who first coined this hundreds and hundreds of years before Dalton, maybe thousands of years before Dalton. And then Socrates and some of those others, they went with him. That they said matter, you can infinitely divide matter. That does not stand up. All atoms of an element are identical in mass and chemical properties, where atoms of a different element differ in mass and fundamental chemical properties. So a chlorine atom is very different than a sodium atom. An oxygen atom is very different than an iron atom. A chemical compound is a substance that always contains the same atoms in the same ratios. So we might talk about, we already talked about it a little bit, pure substances. Compounds and elements are pure substances. And how does a pure substance differ from a mixture? A mixture has variable composition. So water is always 2 hydrogens to 1 oxygen, and that gives it constant composition. In chemical reactions, atoms from one or more compounds or elements redistribute or rearrange in relation to other atoms to form one or more new compounds. Atoms themselves do not undergo a change of identity in chemical reactions. So I'm sure Dalton was looking at a law of conservation of matter. And here's some lead bricks, and here's some gold. And we found out the alchemists wanted to do that, but they were unsuccessful at doing that. Now we might have to modify Dalton's atomic theory a little bit, because there's some things he didn't know about. Under circumstances, some atoms can be divided, split into smaller particles. You might have heard of the atomic age, the splitting of the atom. Well, that's in nuclear reactions. And we're just looking at chemical reaction. Not all atoms of an element must have precisely the same mass. So here are some isotopes of carbon. We'll talk about isotopes more at the end of this chapter. So carbon-13 is heavier than carbon-12, and carbon-14 is the heaviest. About 1% of the carbon on the Earth is carbon-13, and you might have heard of carbon-14 dating. And what we have on the periodic table under carbon, you'll see 12.011. That's the weighted average of all these. And of course, John Dalton had no way to realize all this was occurring. Atoms of one element can be transformed into another through nuclear reactions. I talked about that uranium up there. Uranium can undergo a bunch of decay processes and turn into lead 208. And then in a particle accelerator, like they might have at Los Alamos, you can transmutate one element into another. But it takes a lot of energy and you only get small amounts. And those are nuclear reactions, not chemical reactions. All right, here's Mr. J.J. Thomson. And we might say he discovered the electron. And he discovered that electrons are negatively charged. And electrons are much smaller and lighter than atoms. And we find electrons in a bunch of different kinds of substances. He proposed that atoms must contain positive charge that balance out the negative charge of electrons. How did he figure this out? Well, back in his day, they've been blowing glass for a while, and they were able to make a good vacuum pump. And so if you suck all the air out of here, you'll think you'll have all the air out, but there'll be a little bit of air. And maybe your grandparents or somebody had an old television or radio and it had vacuum tubes in it. Or maybe you're a musician with a guitar amp and you like the vacuum amplifier sound. So in a high vacuum with a little bit of gas molecules in there, electricity can do interesting things. And so they had a vacuum tube, kind of has a wire that heats up, makes a cloud of electrons. Then you can accelerate that into electron beam with some plates. Like here's some plates to accelerate a beam, and something's getting heated up, making electrons. And when this electron beam goes through the gas, it lights up kind of like a neon light. In lab, you'll play with some discharge tubes and you'll see what I'm talking about. And then he would put a electrical potential out of here, and he saw that the beams were deflected. And when this goes negative, it's deflected down here. When it's positive, it goes up there. I'm kind of out of sync. Positive up there, negative down there. And we know that like charges repel each other. Opposite charges are attracted to each other. I think in Alex you do a bunch of little things with charges. It'll be good for you. So he came up with this thing called the plum pudding model. How many of you eat plum pudding? Nobody. It's something they do over in England. I would call it the raisins in your oatmeal model. He was eating his plum pudding one day and he said, well, I got to put electrons somewhere in the atom. And he proposed that the atom must have a positive nature, and these electrons he imagined as particles, and he had to put them somewhere. So the plum pudding model suggests that negatively charged electrons were held in a sphere of positive charge. And I just noticed the colors are all messed up. Maybe you're colorblind and didn't even notice. So that's how he discovered the electron. He came up with this plum pudding model. The next fellow that came along was named Ernest Rutherford, and he did this famous experiment, or his lab student did, with gold foil. So gold foil, you can hammer it so thin you can see through it. It becomes transparent. And he got this thin piece of foil, and here's a lead block, and he put some radium back there. Now radium's radioactive and emits alpha particles. Alpha particles are helium nuclei. Maybe they didn't understand all these nuclear particles so well, but they knew how to get a beam of this going. And here's a plate or film that has phosphorus on it. And when one of these charged particles hits it, it lights up. So his lab assistant sat in a dark room and watched these flashes and kept track of them. And what'd they figure out? Here's what Rutherford expected. Here's the plum pudding model. You can see all these bowls of plum pudding. He expected these particles to go straight through. What Rutherford actually observed was that, yeah, indeed, a lot of the particles went through. 98% of the alpha particles went straight through, but about 2% of the alpha particles went through but were deflected at large angles. Here's the large angles, and about 0.01% of the particles bounced off the gold foil, like that. and they were astounded. They say it's as if you fired a 15-inch cannonball shell at a piece of tissue paper and it came back at you and hit you. Came back and hit you. So then Rutherford had to say, well, what does this tell us about the atom? So the plum pudding model went away, and we say Rutherford invented the nuclear atom. Nuclear in that it has a nucleus. What is a nucleus? That's home of some subatomic particles called protons and neutrons, and we figure out that the atom is mainly empty space. Most of those alpha particles went straight through, and if an alpha particle is positively charged and this is deflected, that means the nucleus must be positively charged. And I think I'm getting ahead with my speaking for the next slide. Here's the take-home message with the Rutherford's experiment, what we learned. Most of the atom's mass is in the small, dense region known as the nucleus. The nucleus is positively charged, and the rest of this must be empty space. So it turns out they hadn't done an experiment about the electrons and didn't know what to do with the electrons, and so they said, well, the number of negatively charged electrons outside the nucleus is equal to the number of positively charged particles, protons, inside the nucleus. Now, Rutherford didn't know what a proton was yet. That came a little bit later, but they knew what electrons were, and they knew that, you know, a gold atom is electrically neutral. So there had to be an equal amount of negative charge to positive charge. So electrical charge is a fundamental property of protons and electrons. Positive and negative electrical charges attract each other. How many of you like dryer sheets? I hate them. Mainly because my wife makes me do laundry and they're always falling out everywhere. And they're probably bad for you. We just probably don't know it yet. But it's better than static cling. So static cling is when you have like cotton and then you have like polyester and they develop a charge and then they stick to each other. So you pull out a shirt to fold it and stalks are stuck on it. I don't ever have to do that. I just have to deal with dryer sheets in the bedroom, in the hamper, just showing up everywhere. Positive and negative charges, positive, and negative charges repel each other. Here's where I say like charges repel each other. Positive and negative charges cancel each other out, so a proton and electron, when paired, are charge neutral. Easy as integers in algebra class, right? Positive 1 summed with a negative 1 equals what? 0. So after the turn of the century, early 1900s, some of these were more formally figured out, the proton and the neutron. Look at these masses in kilograms. 1.67 times 10 to the negative 27th. Now that's an itty bitty number. And here's a neutron, 1.6749, so it's a little heavier, times 10 to the negative 27th. Well, those numbers are nice and are probably interesting how they figured them out. Here's this thing called an atomic mass unit. And sure enough, we see that a neutron is a little heavier than a proton, but for the most part, to like 3 digits, they weigh the same. Roughly just 1 atomic mass unit. Where did the atomic mass unit come from? It comes from assigning carbon 12. Let me write it over here. One C12 atom weighs 12 atomic mass units, and everything else is kind of based off of that. And I'll have a whole lot more to say about carbon 12 in upcoming chapters. Oh, one more interesting thing here, the electron. It is like 55,000 times less massive than the neutrons and protons. So an electron has very, very small mass. Electrons almost have negligible mass. Almost, not if we can measure it. So there's this thing called the atomic number. Let me write carbon's atomic number down. Atomic number 6. And if you look over there on the periodic table, you see the 6 written up in the top right-hand corner. And it's the number of protons that give the identity of the element. If it has 7 protons, it's not carbon but nitrogen. And oxygen has 6 protons. So if I find helium over there, I see atomic number 2, meaning 2 protons in a helium nucleus. Aluminum, how many protons does aluminum have? Find it over there on the periodic table, and you'll see it 13. So the atomic number gives us the number of protons inside the nucleus of an atom, and it gives the identity of that element. That's what identifies one element from another element. It's the number of protons in the nucleus. And for fun, we give the atomic number a symbol. We call it Z, after Gen Z, no doubt. So there's the 6 I was talking about. There's the 7. Here's beryllium. So on a periodic table, you get a lot of information. Atomic number. I'd really like to say atomic weight. We can use mass. The name and how they're all laid out. So chlorine must have 17 protons in it. Neon must have 10. So the origin and names of the elements. Most chemical symbols are based on the English name of the element, like C for carbon, N for nitrogen, F for fluorine. Those are pretty straightforward. But then there's some that are kind of messed up in that we don't speak Latin, do we? So some Latin names. The symbol for potassium is K from the Latin kalium. Same thing for Latin for sodium, natrium. How many of you have heard of Natrona? We live in Natrona County. That's because there's a lot of sodium in our ground, probably sodium carbonate. Additional elements with symbols based on their Greek or Latin names include the following. PB for lead, and everybody can tell me what a plumber is. So the first plumbing, we like to say the Romans. We're pretty modern, and the Romans had indoor plumbing. What did they make their pipes out of? They made them out of lead. And there's theories that, when you get exposed to lead, it messes with your mind. It stops development in small children. That's why you don't want to have an old crib painted with that nice yellow lead paint, which is sweet. Lead acetate, if you taste lead acetate, is sweet. So the Roman Empire fell eventually, and some historians say the lead exposure, the aristocrats and people in power went crazy and mad due to all the lead, and that helped them blow up society. Mercury, Hg, ferrum for iron, Ag for silver, Cu for copper, Sn for tin. So what you want to bone up on the periodic table is the ones that aren't logical, like the lead and mercury, potassium. My favorite true and false question to put on a quiz is like, P is the symbol for potassium. No. S is the symbol for sodium. No. We got phosphorus and sulfur, not to be confused with K and Na. Then copper's kind of reasonable, unless I give you CO. Is CO the symbol for copper? No, cobalt. And then if it's CO and they're both uppercase, that's carbon monoxide. A lot of fun things there. Early scientists gave newly discovered elements names that reflected their properties. Argon from the Greek argos, which means inactive. Now we call them noble gases. Older periodic tables called them the inert gases. And then chemists started making xenon and krypton compounds. Other elements were named after countries. Polonium after polonium, francesium after France, americanium after the United States. There's berkelium up there. And then, of course, my favorite is there's some einsteinium up there. Here is CM curium. It's named after Marie Curie, a chemist who helped discover radioactivity. She also discovered 2 new elements. Curie won 2 Nobel Prizes for her work. And then bromine originates from the Greek word bromos, meaning stench. So here's kind of a monument over in Eastern Europe somewhere, Dmitri Mendeleev. And he's the famous chemist that gets all the credit for the periodic table. At his time, there's like 2 other people coming up with a periodic table, but they weren't as bold as Dmitri. Dmitri laid out his table. He noticed that every so often elements had similar properties. How many of you get a periodical? How many of you know where the periodical section is in the library? We're going to figure out what the word periodic means. So periodicals, you come out like once a month or once a week, periodically. And that's what Dmitri noticed. Every so often, the properties of an element repeated themselves. That when the elements are arranged in order of increasing relative mass, certain sets of properties reoccur periodically. Periodically go to sleep. Normally at night. Happens about 365 times a year. So here's a picture of possibly Dimitri's periodic table. Here's hydrogen. Next thing up is helium. And then lithium, reactive metal, inert gas. Sodium, very reactive metal. And magnesium acts a lot like beryllium. Sulfur and oxygen, form similar compounds. Let's just look at some of these. My favorite, sodium chloride. Well, lithium chloride looks very similar, 1-to-1 ratio. And then my favorite compound with oxygen, I'm going to just draw the model. So these have similar shapes, similar bonding. Sulfur likes to have 2 hydrogens, oxygen likes to have 2 hydrogens. And we can look at a few more of these. Nitrogen likes to bond with 3 hydrogens. Phosphorus likes to bond with 3 hydrogens. And we could do something very similar here with, in the lab, you dissolved up some calcium chloride. What do you think the formula for magnesium chloride is? You're going to invoke the law of periodicity. Well, if calcium likes 2 chlorines, then magnesium's going to want 2 chlorines. And then we can probably figure out what beryllium chloride's going to be. How about potassium chloride? So similar properties, 1-to-1 ratios, 1-to-2 ratios, maybe 1-to-3 ratios, 2-to-1 ratios. So Dmitri put them in rows so that similar properties align in the same vertical columns. And I was saying, what made Dmitri so famous, his periodic table had some holes in it. And people said, why does your periodic table have these holes in it? And he said, well, these are just elements that haven't been discovered yet. How do you like that? That's really what we like in science. You make a prediction, and they're like, what? You think some element exists that hasn't been discovered? What are you, all-knowing? Sounds kind of blasphemous. And then he said, not only that, I'll tell you its density, and I'll tell you what type of compound it's going to form with oxygen. And then he was proven true. Those elements were discovered. They had the chemical bonding that he explained and some of the physical properties like density. He nailed it. And so he gets all the credit. Dimitri's periodic law was based on observation. Like all scientific laws, the periodic law summarized many observations, but did not give any underlying reason for the observations. Only theories do that. That goes back to something we learned about the first week. So here we see another periodic table. And here's one of the most important things to figure out. Metals are over here on the left, and there's way more metals than nonmetals. Here are the nonmetals, and there's this diagonal stair-stepping line that separates metals from nonmetals. And some of these things that are adjacent we call metalloids or semi-metals. They have properties of both a metal and a non-metal. Any electronic buffs in here? Here's germanium, arsenic. Has anybody heard of a germanium diode? How about this? Has anybody heard of a semiconductor? What computer chips are made of? They're made out of primarily silicon, And sometimes man puts a little bit of germanium inside the silicon, and then it becomes a semiconductor. It can conduct like a metal, but with a circuit, it can be controlled, just like a vacuum tube. All right, metals occupy that left side over here, and they all have similar properties, like conduct electricity, conduct heat. We say they're malleable, or they're ductile, can be drawn into wires. I told you the gold could be hammered into sheets so thin you can see through them. Metals are often shiny and lustrous. Now those alkali metals and alkaline earth metals, I gave you a piece of calcium and it looked like it was covered in white fuzzy calcium oxide. And I cut some of those pieces and I might have showed you and you might have looked and saw it was very shiny. We call that lustrous. Metals tend to lose electrons when they undergo chemical changes. This is something you want to put in the back of your mind and never forget. It'll help you a lot in chemistry. Good examples of metals are iron, magnesium, chromium, and sodium. Non-metals on the upper right, they have varied properties, and a lot of them are kind of opposite, like poor conductors of heat and electricity. And so this point and that last point, metals like to give up electrons, non-metals like to take on electrons when they undergo chemical change. Those are the two things you really want to remember. And I've already been talking about metalloids along that diagonal line. Have properties of both, and they're used in the semiconductor industry. Silicon, arsenic, and germanium. Good example of metalloids. I'm going to just jump ahead to my favorite slide. As an example of periodic law, metals like to give up electrons. In this first column, they all like to give up one electron. They all form these ions that are +1. We call them cations. Everything in this column really has 2 electrons to give up, and they become +2 cations. Non-metals like to take on extra electrons. Everything in this column is going to form a -1. Everything here a -2. I'll let you go 2 minutes early.